Hello my dear students, I warmly welcome you to Sia's digital classes. In this lecture, we are going to discuss about the definitions. So let's see the question first of all. Define a ring and commutative ring with unity. Give examples for ring and commutative ring with unity. For the examination purpose, especially in the short answers, these two questions are very important. Okay. So first of all, we have to define the ring, and after that we have to define the commutative ring with unity. So whenever you define any definition in the examination, definitely you have to give at least one example. Okay. So let's see the definition of the ring first of all. Ring, a set, okay, a pair or a set R of R plus addition. Okay, a set capital R is said to be ring with two binary operations under addition, under multiplication is said to be ring whenever if it satisfies the following conditions. Okay, so the set, the mathematical representation you can write R comma plus comma dot. Okay, so in previous lectures, okay, so we discussed that if you take any group or any set, we have to use that set simultaneously only multiplication only or addition only. So now for the first time we are using a set simultaneously with respect to addition and multiplication. So that representation or that pair of R comma plus comma star dot, that is ring under addition under multiplication. So whenever it satisfies the following condition, what are those following conditions are? For all a comma b comma c belongs to real numbers. Here capital R is always real numbers. Okay, for a b c belongs to real numbers. The first condition is R comma plus is an abelian group. That is ring is an abelian group under addition. Okay, so this is the first condition. So in this first condition again we have some properties, four properties. So abelian group. Abelian means a plus b is equal to b plus a. This is the commutative property under addition. Okay, so next associative property, a plus b plus c is equal to a plus b plus c. Next identity condition, a plus 0 is equal to 0 plus a is equal to a. Okay, simply we are writing a plus 0 is equal to a. Okay, next inverse condition under addition, a plus minus a is equal to minus a plus a is equal to 0. Okay, so this is the inverse condition under addition. Whenever any ring satisfies these four conditions under addition, then R comma plus, the pair representation R comma plus is said to be abelian group. Next, the second condition is R is semi group. Okay, semi group is nothing but in the name only we have semi group. Semi is nothing but half. Okay, half of the group. Half of the group is, that is purely associative condition with respect to multiplication. So that is R is a ring under multiplication whenever it satisfies the semi group condition. That is for any three elements a comma b comma c belongs to capital R, their product, associative product is equal to a into b into c is equal to a into b into c. This is the second condition. Okay, so now in first condition R is an abelian under addition. In second condition R is semi group under multiplication. Now the third condition is by mixing both two binary operations R comma plus comma dot is distributive. Okay, so distributives laws you know very well. Okay, so here we have two types of distributives, that is the left distributive law and the right distributive law. So this is the condition for the left distributive law. For a comma b comma c belongs to capital R only. Now a into b plus c is equal to ab plus ac. Next right distributive law, b plus c into a is equal to ba plus ca. Okay, so distributives laws have some significance, that is, so these laws we can use simultaneously two operations, that is addition and multiplication. Okay, so if you multiply small a on left side, it is called left distributive law. If you multiply small a on right side, it is called right distributive law. Whenever any set capital R satisfies these three conditions, the first condition is r comma plus is an abelian group, okay, and r comma dot is semi group, and r comma plus comma dot is distributive group under addition and multiplication. Then the pair representation r comma plus comma dot is called ring, okay. So this ring, the word first, okay, first used by the famous German mathematician David Hilbert in the year of 1897, okay. In the year of 1897, the famous German mathematician David Hilbert was used the word ring, okay. He gave the name of that property. Before him, okay, in the middle of the 19th century, that is 1850 around, the famous mathematician Richard Dedekind, okay, another mathematician is Richard. Another mathematician is Richard Dedekind gave the algebraic notion for this ring. That means he developed this concept. If you use multiplication, addition simultaneously for a set, what will happen? He thought in that format, and he discovered this type of concepts, okay. After him, in the 1897 year, the mathematician David Hilbert gave the name for this property as a ring, okay. From then, so we are calling this property as a ring, okay. So this is about the ring condition. Next, commutative ring with unity. So in the name only clearly we have, so this property you know very well, commutative property, okay, and ring already we discussed now only with unity. So okay, in this word only, in this definition only, we have three definitions: commutative, ring, and unity. So you know very well commutative property, okay, it leads to the abelian group, and ring already we discussed that, and unity is not an identity, okay. There is a difference between identity and unity. Unity is a non-zero word which has multiplication identity, okay. Unity is a non-zero element, non-zero word, non-zero element. That element definitely should have a multiplication identity. Then that element is called unity. So now commutative ring with unity is nothing but a ring, okay. So capital R is said to be a ring, capital R is said to be commutative if A comma B belongs to capital R, A into B is equal to B into A. So this is the condition. And next, ring with unity. So if you take 1 belongs to that ring, okay, 1 belongs to that ring, then 1 into A is equal to A into 1 is equal to A in place of B, okay. In place of B here, we are substituting 1. That 1 is the fixed element, and if you take any other element in place of A, then 1 into A is equal to A into 1 is equal to A, then that ring is called ring with unity or commutative ring with unity. For the definition purpose, in the examination, these two definitions are very, very important. Now, we are giving the examples, okay. So, first example is the set of integers. You know very well, okay, for 0, plus or minus 1, plus or minus 2. The set of integers is a commutative ring. Ring and a commutative ring with unity under addition and multiplication. Why? Because if you talk about ring, so you have to talk about the addition and multiplication. Not only addition, okay, but also multiplication also. And the set z suffix n, that is equal to 0, 1 up to n minus 1. The set of the subset of integers, that is z suffix n, is a commutative ring with unity 1 under addition and multiplication, okay. So next set is z of x, okay, z of bracket of x, okay. Z of bracket of x, you can call it as a group of polynomials with integer coefficients. Whenever you have a representation in this format, that belongs to polynomials group, okay. Group of polynomials with if you have z here with integer coefficients, if you have r here, capital R, so the group of polynomial with real coefficients, okay, real number coefficients. So in that format, the set z of x of polynomials in capital X with integer coefficients under addition and multiplication is a commutative ring with f of x is equal to 1, okay. The polynomials exist in this format with unity, f of x is equal to 1. Here whenever you write f of x is equal to 1, then you can call it as a constant polynomial. Okay, so f of x is equal to 1 is nothing but constant polynomial. So those types of polynomials will exist in the group of that polynomials with integer coefficients. So that is also a commutative ring with unity. Next, we are talking about matrices, the set of 2 by 2 matrices. Okay, here capital M2, M suffix 2 of Z. Capital M represents the matrix. Okay, suffix 2 represents the order of that matrix, and Z represents that integer. Entries in that matrix belongs to integers. Okay, the set of matrices of 2 by 2 with integer entries is a non-commutative ring with unity 1001. Okay, it is non-commutative ring. So you have to give these types of examples also in the examination. Okay, so this is another example. So this is the non-commutative ring with unity. So why? Because 1001 is the identity element in that set. Next, the set 2 into Z. Okay, so you know very well Z, and if you multiply with the two integers, then you will get all even integers only. Okay, so if you multiply with the two only, there is no no odd integers. You will get all even integers. The set of even integers under addition and multiplication is a commutative ring without unity. It satisfies the commutative ring property without unity. Why? Because if you multiply with the 2 for the integers, then you will not get the number 1. 1 into 2, again you will get 2 only. Okay, so therefore without unity only they will satisfy the commutative ring property. So in these examples we have discussed the commutative ring with the unity examples, and non-commutative ring with unity examples, and commutative ring without unity examples. Okay, these 5 examples are very important for the short answer purpose. Okay, so this is about the definitions of ring and commutative ring with unity. Okay, I hope you understood this lecture very well. In the next lecture, we are coming with another new topic. So, make a perfect practice, prepare well. Until bye, thank you.